Hello, welcome back. We've got about an hour and 20 minutes. And in that time, I will demonstrate setting up SnowStorm Lite, which is an API that you can use to query SNOMED CT. And then we'll do a Python data science exercise. I will share my whole screen. Okay. So Snowman International produces two terminology servers. And a terminology server is a good way to query SNOMED in like a standardized way. I produce both of these terminology servers. The SnowStorm server is the big version. It has two different APIs. It has the Fire API, which we recommend, and it also has a specialist SNOMED API. This SNOMED API is the backend for the SNOMED browser. All these additions are stored on one instance of SnowStorm, and it allows us to do some specialist SNOMED things, but it's not really standardized, and it changes frequently, this API. So we always recommend for data scientists or any other implementers, if they can, to use the Fire API, because it's standardized and it hardly ever changes. So as I said, there's two versions of SnowStorm. There's the big SnowStorm that allows you to load multiple releases of SNOMED CT. You can store many at once. You can also load LOINC, ICD-10, ICD-10, CM, and many other code systems into the main SnowStorm. It requires quite a lot of memory. It uses Elasticsearch. It needs at least 8 gigabytes of memory. Yeah, so that's one option. The second option is SnowStorm Lite, which is a relatively new product. It was developed last year because we were doing some integration with an EHR that's often deployed in remote areas of Africa. But I realized that there's an opportunity here because we can produce a SnowStorm server that just has one API, the Fire API, but it's actually much smaller. It just requires 1 gigabyte of memory to run on your machine. But it's actually, because it's doing less, it's more optimized. It runs a lot faster than the SnowStorm API. The big SnowStorm API is also used for authoring SNOMED CT, for modifying it and branching it. So when Maël and Elizabeth are working translating the French edition, they're using the SnowStorm API. So it has a lot of jobs. So it's difficult to optimize it because it has so many different jobs. The SnowStorm Lite is highly optimized really for query. You can only store one version of SNOMED CT in it at a time. If you need to store a new version, then you just need to load a new version in and it will forget the old version. But it is small and fast. So I'm going to demonstrate setting up this terminology server, and then we'll use it for some querying. The easiest way to run it is in Docker, the simplest way. So I've installed Docker locally. I've started it so that it's running. At the moment, it's kind of empty. I haven't got any containers running. So if you install Docker, which obviously can run on any operating system, then you really just need to run a couple of commands to load SNOMED, or to run SnowStorm Lite and to load SNOMED. If you use there's two ways of loading the data. You can either pull the data from an online service, and there's Snowman International has like a distribution service for SNOMED CT. And if you have an account for that distribution service, you can use this method. The other way is to have SNOMED downloaded and to push it into the API. It's like uploading. So that's this method here. For today, I'm going to use the pull method, pulling SNOMED into SnowStorm. First of all, we need to load SnowStorm Lite, the software, into Docker to make it aware. So I'm going to go to the command line. I am on a MacBook, so I'm going to open the terminal command. And it doesn't really matter where I am because we don't need to use any files. All this stuff just goes straight into Docker. I'm going to just do this really quickly just to show how it works. But for the exercise that we'll do in a moment, we'll actually use an online version of SnowStorm Lite. So you can set up SnowStorm Lite locally later if you want to, but there's no need. You can still do the exercise without it. So I'm going to run this command anyway, docker pull. So this is pulling the software from Docker Hub, where it's published, into your local machine. It hasn't created the software yet. It's just like downloading the CD for installing the software. It's like the setup program. Then this next command will actually deploy it into your Docker. And you'll see here that there's a URI. This is like the identifier for what version of SNOMED I want. And there's a list of some different URIs here that you can use. The URI we're using is the International Edition. There's a couple of others here, but there'll be a new one for the French version. So you'll have to use a different URI to pull down the French edition. I'm going to use this one today. I'll just paste the command, hit enter. And then SnowStorm, and we see up here, SnowStorm is starting up. And we'll see in Docker, if we look, we have a new container running. It doesn't have a nice name, but it's running on port 8080. And it's asking me, because I use the MLDS distribution option, it's asking me for my credentials. I'm going to paste or type them in, and then it started downloading. So it's pulling the International Edition. It's around 500 megabytes, and it looks like I'm not on a very fast connection, so I won't make you wait. But essentially, it's going to download the package, and then it will take about a minute to load the package into the, it uses like a Lucene index, and it will index in a way that searching and running ECL would be very fast. And then you'll be able to make API requests and get the content back. So I'm going to leave that running now, and I'm going to show the online version of this service. It's SnowStorm Lite dash some URL, which I'll paste to you. It's hosted on Google App Engine. Where's the chat? So this is an online version of SnowStorm Lite. This application has auto scaling switched on. So in a few days, if you're welcome to use this like for general use. If you decide that you're going to do a lot of SNOMED queries, then I recommend deploying your own version or running it locally, but you're welcome to play around with it. When you make a request to the service, the first time that day, it may take a little while to respond, maybe 30 seconds or something, and that's because the application scales down so that there's no applications running, and then as it gets more requests, it brings more and more copies of that application online to deal with demand. So the first time we hit it, it might be slow, but then the rest of the time it'll be fast. Okay, so that's SnowStorm Lite. Now let's do an exercise. Oh, I'm going to pause for questions, and then we'll get onto the exercise. Is there any questions about SnowStorm or SnowStorm Lite before we move on? Nope. Yeah. Can I give you a mic?
So on SnowStorm Lite, we've got the whole SNOMED database. Okay, so it's not. We've got all the content. So what's again the difference with the SnowStorm server? Why does it use so much more resource if the whole database is there?
Okay, good question. Yeah, SnowStorm Lite's really been optimized for querying. So everything's stored in a really small and efficient way. We don't record all the information in SNOMED CT. We do record all the concepts, whether they're active or inactive in all the hierarchies. We record all the descriptions. We don't record inactive descriptions. When the reference sets are published, they're all published with a UUID, and there's millions of them in SNOMED. We don't store them because they're never needed for query. Whereas in the big snowstorm, we have to record every data element in the whole of SNOMED CT, and we have to store it in a way that isn't optimized because it's got to support creating extensions and changing SNOMED. And it also has a branching mechanism because when authors work on SNOMED, they want another copy of SNOMED that they can edit, and then they promote their work up through a GitHub branching mechanism. So all that stuff is supported in SnowStorm. That's why it needs more resources. Let's have a look, see if it's finished loading. It has. Oh, question in the chat. There's a hand up, I think.
Hi.
Oui, si vous avez une question.
Hello. Yes, I have a pretty pragmatic question. Will the online version will be available forever or for a long time, or is it aimed to be just a demo, a temporary demo, or thing like that?
The URL may change.
Okay.
It's been online a year, and I intend to keep it online at least another 2 years. SnowStorm Lite itself at the moment is in a beta status, but I know that a lot of people are using it. So soon we'll change it to a proper out of beta product. It is really easy to deploy yourself. You could deploy it into App Engine, or Google App Engine, probably within an hour. Drop me an email if you want a hand doing that, and it costs next to nothing. I think it's costing me about $7 a month to host. Usually it's less because it doesn't get much traffic. But yeah, if you want one that's going to stay up forever, hosting your own is a good option. I do need to send the new version of SNOMED to it, and I do that manually at the moment every month. But I'm thinking of creating some sort of script to update automatically. Yeah.
Okay, thank you.
Question, thank you. All right, so this one's loaded on my local machine, so I'm able in the browser to go to localhost 8080/fire, and I can list code systems, although there's only one loaded. It's the June release of the International Edition. Be nice to have an International Edition label here, but that name International Edition isn't actually in the RF2 files. So we've just got the module identifier here. Maybe I could look up the term from the module, I'm not sure. But essentially, this is the same API as the one we've got up here in Google App Engine. We can just list code systems. And again, we've got the June release. So let's use this one. Okay, so I'm going to step over now to the data science exercise. And if you're familiar with Git or GitHub, I'd like you to download this repository. It's got some Python scripts in it. If you're not familiar with Git or GitHub or Python and you just want to watch and follow along, that's fine too. Let me paste this link into the chat. Yeah, so the GitHub IHDSDO, there's one called SNOMED Data Science Exercise. I've pasted it in the chat. Alternatively, if you go to GitHub, go to IHDSDO here, and you can search data science. Okay, so if you download this repository, the main branch, in here we have some synthetic data that has been generated by the same script that we used for the data analytics demonstrator that we showed. It's also being converted using a conversion script, which is here, prepare data. Because the data analytics tool generates like a JSON format or ND-JSON. And we want CSV so that we can load it into data frames and, normal data science stuff. So it's been converted. And then we have a list. I think there's around 1 million patients in there. We'll go and look in a minute. And we've got events for those patients. I've given it a very generic name, events, because it could be drugs that were prescribed. It could be observations or findings from the patient. It could be disorders with the patient, something that's gone wrong. It could be procedures, all sorts. I've basically bunched them all into one file because we can with SNOMED, we can separate them out again using queries, and it just makes our life easier. So that's the format of our synthetic data. Another couple of things to draw your attention to. We have this class here, which is like a fire terminology server client. It's like a way we can make ECL requests to SnowStorm and get back a set of codes. And it's using, under the hood, it's using the value set expand operation that we saw when we took a look at the Fire API slides. So it's doing value set expand for us, but it's kind of wrapped up into a Python method so that we can just call a method. We don't have to write out the URLs and everything. What else is there to say? Yeah, so there's a few methods in here. I tried to find like an off-the-shelf client for fire terminology services, and there are some around. I was getting frustrated. In the end, I just wrote this very simple client. It's kind of nice to have a really short client like this because we can see exactly what it's doing. It's doing the value set expands. Sometimes when you expand a value set, you get like several 100,000 codes, for example. It could be very big. That's an extreme example. SnowStorm Lite, I think, returns maybe 100 or a few hundred at a time. So you do need to fetch multiple pages from the API to get them all. So this method does that. It will just keep fetching them until you've got everything. So that makes it easy. So that's the Fire client. And then we have the main script here. So I've opened this in PyCharm, which is what I use for Python development. I'm just checking that I'm on the right branch. I am. So there's two options. You could run SnowStorm Lite locally, and on line 10, that's what we have by default to run it locally. If you're running lots and lots of queries, it will be faster if you run it locally. If you're only running a few, this script only really runs a few. Then use the online version. It's less setup. So I've commented out line 10, and I've uncommented line 12 because I want to use the online version. I'm wondering if I should make this bigger. Increase font size. Just a little bit. So the intention of the script is to reproduce one of the data analytics scenarios, and it's the COVID scenario that we showed or that we talked through earlier, where we have a set of patients who have COVID detected, the virus is detected in their body, and we want to find out what disorders have the strongest correlation with COVID pneumonia and of death. And we have a very similar data set in here. The numbers won't match exactly because I ran the generation algorithm again, but it's pretty similar. So I'm going to talk through the code and then we'll run it. And the code only goes part of the way to the solution. I want you to add a bit more. So follow along with me. So we start off by loading the events data into a data frame, and we load the patient data into a data frame, and the events have a patient ID, so they can be mapped to the patient. It'd be nice to see a sample of this. Okay, so these are the events. They've got a patient ID, and it just sort of goes up with numbers. There's a date that the event occurs. That's not actually used in the script at the moment. And we've got SNOMED code, and they're a whole mixture of different things: findings, disorders, procedures, drugs, other things. And in the patients, we have just the patient ID, the gender, and the date of birth, so that we can have an estimation of the age. So that's our data that we're working with. If I was better at Python, I would find out how many are in there. Or if I had a workbook running, I could run just a few lines of code, but I don't know how to do that in PyCharm. I'm still new to Python. I'm going to default to the command line because that's what I know. I'm going to go into my PyCharm projects, SNOMED Analytics, and into the synthetic data. I just want to know how big these files are. I can't remember. Okay, so patients, we have, it's similar to the analytics tool, 1.2 million patients, and the events, about 2 million events. So I guess they've got nearly 2 events each. It's quite low numbers. I think some of the patients only have 1 event. Maybe it's a vaccine or something, I'm not sure. Okay, so that's the data we're working with. And then we've got this method that allows us to filter events using a SNOMED query. And it doesn't just return the events that match. What it does is it runs the SNOMED query, gets all the SNOMED codes that match, then it filters the events based on those SNOMED codes and gets back to the patient identifiers. And then finally, it returns all the events for those patients that match. So we're not just filtering events, we're really filtering patients here. We'll get back all the patient events if they've got some event that matches the query. I hope that makes sense. So then we can go on and use that. So we can create a cohort of patients that we're interested in. We're not interested in the whole million patients. We only want the ones who've got COVID detected. Now I've put in here the SNOMED codes, which I've got from the browser actually. So my method was to go to the browser, look up the COVID detected, because that's I know in my data that was the concept used to record when there was a positive response. This one, and then I've used this arrow here, and we can copy the FSN term and the concept ID, or you could take the preferred term and the concept ID. It's up to you. And once I've copied that, then I've pasted it in here. I think it's important to have both the concept code and the term, so that over time, we can remember what's going on. It makes everything more readable. So I've got the SNOMED code, and I've got the query here. And if you remember, the double less than means all types of this concept. all descendants and self in the hierarchy. And then we filtered our patients. So we should have a set of patients here that have got COVID detected. If I select the lines, will PyCharm let me run a selection? I've got no idea. I'm sure you guys know. Let's try it and see what happens. Is it going to run the whole thing? Execute section in Python console. Let's try that. No, it worked. All right, so, oh look, we've got our counts here. So total event count was 2 million. Total patient count is much lower than I thought. I'm not sure why that is. Checking my print statements. Don't know why that is. I need to go back and look at that. But the cohort that we've created, the one we're actually interested in, is 450,000. Okay, so that's about what we expect. And then we could, as a reference here to the browser, because one way to record SNOMED codes, instead of just recording the code, if you record it like this, with snomed.info/id and then the code, you can actually open that in the browser. It's like a shortcut, and that will always work. And even if you use a code that isn't in the international edition, maybe it's been created in the France edition, for example, this URL will still work because SnowStorm will actually look up where that code is, and then it will display in the browser what version of SNOMED you need, and you can check what the code is. Let's run this one and try. It checks the latest version of the international first. It's found it, and then it gives us, obviously the URL is massive and you wouldn't want to put that in your code, but these short ones are pretty good. We can always check. So that's the URI for a concept. All right, and there's a reference to the ECL guide in case you need it, but in general, I recommend just doing descendants and self of some concept. Nearly always is enough. Okay, so we're interested in a couple of outcomes, and those are COVID pneumonia and death. And we need to run this selection a few times because, first of all, we've got a patient group of those patients with hypertension. So I've gone and filtered the concept, the patients again, using the hypertensive disorder, using the concept ID. And for those patients with hypertension, I've created another group. We're doing the set theory thing that we saw on the slide with lots of overlapping selections. We're filtering the hypertension group by COVID pneumonia, and we're filtering them again by death. So if patients are in this group, they have the COVID detected, they also have hypertension, and they also have death on their clinical record. So we're going to use these numbers to calculate the percentage correlation. We've also mimicked the data analytics tool in that we've got a selection of all other patients that aren't in some other group, so they don't have hypertension. So I've gone ahead and I've taken the cohort, which are the ones with COVID detected, and I've said, just give me the ones where the patient identifier is not in, that's what this means, is not in the hypertension set of patients. So I end up with the patients on in the hypertension group, essentially. And for those, again, I'm counting how many have COVID pneumonia and how many have died. And we get out all the counts at the end, but I thought it would be nice to put it into a graph. So the following code, I don't understand some of it, but ChatGPT helped. We'll go and plot the graph. I'll go ahead and run that now. If you've got this code locally, go ahead and run it. Yeah, in my day job, I code in Java, writing APIs and things like that. So I'm still fairly new to Python. So here we are, we've got our plot, and we've got the hypertension group and the all other patients group. And the percentages are looking pretty similar to what we saw in the data analytics tool. So I thought it'd be interesting. There's a few things we can do from here. I thought it'd be interesting if you guys on the call could try and create the second patient group. So maybe we use diabetes mellitus, or you could use obesity. I think they're the interesting ones. We could try others, it doesn't matter. And create another group and see what the correlation is for that group with pneumonia, what the correlation is with some other group for death. And also remember to take those patients out of the all other patients section, and then add them to this graph. And let's see what we can do. After that, I've got something else to look at. But let's spend, I don't know how long it's going to take, 10 or 20 minutes. And feel free to ask questions. And I'm going to very slowly do the same thing here. If you've got any questions about the stuff, just shout. I'll send you a link to the browser in case you don't have it. I think I'm going to use diabetes mellitus. I need to pick the active one. If you are picking diabetes mellitus, make sure you select the disorder, not the family history situation or one of the others. How are we getting on? Is anyone stuck? Or is anyone finished yet? I think I've made a selection, but now I need to tackle the graph. Oh, I've forgotten to take my diabetes patients out of the other group. I better do that. if you've started testing your script and you're finding you're getting connection issues, remember to comment out line 10 of the script that says localhost and uncomment line 12 of the script for the app spot. And that will make sure that you're using the SnowStorm Lite online version, and you shouldn't have connection issues. How are we getting on? Do we want another 5 minutes? Or shall I attempt to run mine and see what breaks?
If you have any issue with the script, don't hesitate. We can take some time to look at it and try to find the issue.
Yeah, don't blindly copy what I've done because it could be wrong. Does anyone know a better way of filtering data frames? Here I've, in the example on line 75, I've, to create the other patient group, I've filtered the cohort events by patient IDs that are in the hypertension events, but I need to filter twice if I've got diabetes 2. And I've done this on separate lines, but I wonder if there's a nicer way of filtering by 2 sets at once. I don't know. And. Hmm. This one's not a slight negated. I don't know if it'll work. Oh, okay. Hmm. I think it might be a chat TTP moment. Ah, the ampersand there. Yeah, I see. Okay, cool. That's much nicer. All right, well, I've attempted the exercise. I've got to be honest, I haven't actually done this before, adding another one. I've kind of extended an exercise that I had previously, but I haven't actually tried it. So let's see what mine does. So I've gone ahead and found diabetes mellitus disorder in the browser. I've got the concept code, and I've kind of just repeated what we've done for the hypertension group. for the diabetes group. So I found a set of diabetes patients. I filtered them by COVID pneumonia, filtered them by the death event. And then, where are we? I've created another item in the pneumonia percentage, the second item, and in the death percentage. And of course added them to the category. I think that's all I need to do, but I'm not sure. Let's run it and see what breaks. Okay, I haven't got any errors. Diabetes is showing up on the chart. It's a stronger correlation with hypertension, which is what I expect. And I can see that all of the patients, the dead group has shrunk right down to less than 2%. Again, that's what I expect. So I think it looks pretty good. I could use the data analytics tool to correlate and to check. Something I've just realized we're not doing here is the history supplement, and we probably should be. I can't remember if SnowStorm Lite supports that. I'll try it and find out. I've got an error using the history supplement. Might be that it needs to be URL encoded. Don't know. Let's try it directly on the API. I think it's an encoding issue. Oh. Okay, so I will, we should be using history supplements, and SnowStorm supports the history supplements, but because there's a lot of weird characters, like the double braces, they're not, the braces aren't valid characters in an API GET request. They shouldn't be part of the URL of a web page. So they need to be URL encoded. I will update this exercise over the next couple of days so that the URL encoding happens in the script. It'll be a nicer experience. Okay, so I think I've got a working example. I will share it as a gist, actually, in case you want to look. So I basically copied the whole script again into here. I'll share it in the chat. That's the easiest way, I think. All right, so that's giving you a little bit of practice of create or using SNOMED and SNOMED queries, using fire terminology services. You've seen how to deploy fire terminology services or use a hosted version. I know that ECL seems quite daunting, and there's a lot of crazy things that you can do with ECL, but in general, just picking a focus concept and saying the sentence itself of this, you can do a lot with it, especially once you bring it into Python and use data frames and do some set theory and filter things in that way. There's a lot you can do. So knowing everything that ECL can do is really, I don't think it's necessary. We'll leverage the hierarchy. There's a final thing I wanted to show you. I'm going to stash these changes. I always do this on the command line. There's stash. Okay, there's another branch to this project. There's one more branch. It's called graph clustering. Now, this is the final thing I want to show today. We've got about 20 minutes, so it might not take that long. But I've been doing some research with a group of hospitals in London called Barts Health. And we've been developing a methodology for data discovery in SNOMED coded data. So everything that we've shown so far today, we've had to test some known subset of concepts against the data. We like create a subset, check the correlation, create the subset, check the correlation. We have to know up front what we think the correlation is going to be before we can measure that correlation. This clustering takes a different approach. This is where we don't know what the correlation is. In general terms, we create two groups of patients and we ask the clustering algorithm to discover which SNOMED concepts are most relevant in defining the second group of patients versus the first group. So let's put this into context. It can apply to a few of our data analytics scenarios. I think we've got about 12 different analytics scenarios which are in this data set. I know I've demonstrated the COVID one today, so I'll put it in context of the COVID one. The two groups of patients could be the cohort of patients, like the overall cohort. Again, could be the same as what we've got today. It could be that they've got COVID detected, and the second group of patients could be those who have died, for example. And then we're asking the algorithm to say, look at all the events, all the observations and procedures and drugs and anything else that was recorded in SNOMED, which is in the events in the patient record. Which of them have got a strongest correlation to this second group, which has got a poorer outcome, the patients that are dying? Look through the whole of SNOMED and work it out. And with SNOMED, one of its strengths is its breadth of coverage and also its granularity. You can record, very specific things. But that also presents us a challenge as data scientists, because there's so many different codes in the data that if we just look at the codes on their own, we won't find strong correlations, because the same code might not come lots of times in the data. Because, for example, for asthma, there's 100 different types of asthma. If the clinicians are being accurate and recording all those different 100 types, even if like half of your patients have asthma, looking at the codes, you might not realize. You really need to use the hierarchy. So there's a clustering algorithm here in this graph clustering script, and it takes a few things. It takes the knowledge graph, which is the graph of SNOMED, like the tree structure. It takes a list of all the codes that have been recorded throughout all your patient records. It also takes the different the two groups of patients, and then it attempts to it takes all their records as well, and it basically maps their records onto the hierarchy, and then it tries to figure out what is the lowest point in the hierarchy where you've got a statistically relevant difference between the two patient groups, and it tries to summarize it, and it tries to count it tries to surface the highest number of times a type of disorder or finding has identified with the second patient group. So this is kind of experimental research that we're doing now, and it's still going on. It was originally written in Java, but I've converted it to Python just so that I can, share it with you, maybe get your feedback. So this script starts off in a similar way to the previous version. You can run it against the online version. I've actually deployed SnowStorm Lite locally, which we did it earlier. I think it's still running. Yeah, it's still running. So I'm going to run this now. It's the same data set. So what we're doing is we're defining the set of patients who have COVID detected. We've also got the set of patients with COVID pneumonia and the set of patients who died, but we haven't started measuring obesity and diabetes and hypertension. We're not doing that. We're just going to give it to the clustering algorithm and see what it can discover in the data set. It looks like we're working on half of the data. We've done like a sample because 1 million patients, the algorithms will take quite a few minutes to work through them all. We could give it all of them, but we're doing a data sample here of the first half. And then we've got two groups of patients. The first group don't have death on the record, and the second group do. They've all got COVID, but only the second group have got death. And then we will create the graph clustering instance, and then we'll run it. We're also giving it an instance of the terminology server client so that it can make all the requests at once against the terminology server. I'm going to run this now. So it starts off by finding what are all the unique SNOMED concepts in all the events across the dataset. And for each SNOMED concept, it's loading what is the parent concept and what is its parent concept. And so it can find all the parent links, and then it can reconstruct the tree of SNOMED in memory, not the whole tree, just the tree of SNOMED that's relevant to this dataset. So there's a lot of queries going on, which is why I tend to use a local SnowStorm instance. It's just a bit faster. There's less latency. It works against the online version, but it's just a bit slower. Okay, so that's finished. And then it will take about 2 minutes, I think. It's identified a couple of concepts in this data set which haven't been found in SNOMED CT. I expect those codes have been made inactive. At the moment, this algorithm doesn't do very well with inactive codes, so there's room for improvement. Let's look up these codes. See what they are. All right, I'm searching for active concepts and it's found nothing. So I'll go for both, active and inactive. Yeah, it was made inactive. Some type of ulcer. It's a very complicated disorder, that one. You can see in the history that it was made inactive in this last release in June. Okay. we can actually look at old versions of concepts. For example, if we click this one, that's brought us back to the 2021 version when this concept was active. I'm going to switch back now. So it's gone ahead and it's ranking all the nodes in SNOMED to find out which are most relevant for determining group B. Still running. So it starts off right at the bottom of the tree and it works its way up, and there's a little bit of a trade-off between being very specific and being too general and not really very interesting, because although the very specific codes, you know, the ones on the records, there might not be enough grouping to be able to create some like logical, you know, grouping of them. So the algorithm starts walking up the hierarchy, but we've got to put some weighting in there to try and push it down the hierarchy, because otherwise the algorithm will always go all the way up to SNOMED CT, which is not very helpful. So there's some weighting in there to try and you know, push it lower to give us some good summary nodes. All right, so the algorithm's finished. I didn't tell it what the criteria was for selecting group A and group B, and it's told me that the score of the concept pneumonia caused by COVID is the highest one in determining group B, which is interesting. The reason it's gone above 1 is because the boosting that I talked about. It's possible to, it's like more than a whole. This is because of the boosting. The second one it's surfaced is dead. And of course, these groups are defined by this, the second group is the patients who are dead. So these two are not useful whatsoever, but the algorithm didn't know because I didn't tell it. The next 3 it's given are really interesting. So this is saying just over half of all the patients in group B have diabetes mellitus. And this code for diabetes mellitus isn't used in the dataset, doesn't occur in there. I think, I don't know how many types of diabetes there are in SNOMED, but those, you know, codes down the hierarchy were used. But the algorithms, you know, summarized them up to this level of diabetes mellitus. And it said if you wanted to, you know, create some rules or a patient pathway or clinical decision support rule, or, you know, whatever you're doing, diabetes mellitus is a good node to pick, to say that, you know, if they've got this, they're you know, 54% likely to go on to establish death. You know, there's a really strong correlation. And again, it's got slightly lower correlation for obesity and around 0.3 for hypertension. So yeah, this is a nice way of doing data discovery using clustering. We're still using the SNOMED hierarchy, but we're not firing lots and lots of queries. We're just kind of loading everything into a tree and doing a kind of diff and summarization operation. So yeah, that code's there anyway in the repository. You're welcome to play around with it or send me feedback. It is an experimental algorithm, but I think it's still interesting. Yeah, that's everything.